So, welcome to this. This is our fourth half-hour lecture on dimensional analysis. I had in the beginning explained to you the fundamental dimensions, the derived quantities, how to calculate the dimensions of the derived quantities, and we were looking at some examples where we can use dimensional analysis to advantage in reducing the number of parameters in a problem. If a problem contains n parameters and there are m dimensionless groups amongst all of those parameters, the number of non-dimensional quantities is just n minus m, and that can greatly simplify problems in many situations. We had looked at the case of a particle settling in a fluid, in which case the drag force non-dimensionalized by the viscosity, velocity and diameter depends only upon one non-dimensional number, the Reynolds number, in addition to the aspect ratio, for example, the ratio of the diameter of the particle to the size of the system. And most recently we were looking at the heat transfer in a heat exchanger, where we had identified the dimensional groups. Okay. The number of dimensional groups is quite large. It is 9 in this case. The heat flux is the dependent dimensional quantity. Okay. It depends upon the temperature difference between the shell and the tube side, of course, the average temperature dependence, the length and diameter of the tube, thermal quantities, specific heat, thermal conductivity, mechanical quantities, the velocity, the density and the viscosity. Okay. And so there are a total of 9, and there are 4 dimensions in this problem: mass, length, time and temperature. So simplistically you would think that there should be 5 dimensionless groups. However, in this case we had made a simplification. We had said that there is no interconversion between thermal energy and mechanical energy. Okay. And when there is no interconversion between thermal and mechanical energy, we can consider the thermal energy to be a separate dimension in itself and express all the thermal quantities in terms of this thermal energy. Okay. In this particular case, the thermal quantities were the heat flux, the specific heat and the thermal conductivity. The thermal conductivity, the specific heat and the heat flux were thermal quantities. And so those alone we had expressed in terms of the thermal energy, whereas mechanical quantities were expressed in terms of mass, length and time. And on that basis we had derived a total of 4 dimensionless groups. Okay. The dependent dimensionless group is a non-dimensional heat flux. Okay. It is called the Nusselt number. Okay. The Nusselt number is a non-dimensional heat flux, okay, which is Q d by K delta T. Okay. That is the dependent. Okay. What you want to measure or what you want to estimate is the heat flux. When you non-dimensionalize that, that is the dependent quantity, the non-dimensional heat flux. Okay. And this is some function of d by L, rho u d by mu, Cp mu by K. Okay. The first one we know, okay, is just an aspect ratio. The second one is what we have seen earlier in the earlier lecture, the Reynolds number, ratio of fluid inertia to fluid viscosity. The third one is, you can see it contains both thermal and mechanical quantities. Okay. It is called the Prandtl number. Okay. Cp mu by K. Okay. I will show you later that it is a ratio of diffusivities for momentum and for energy. Okay. So, we have got now the dependent quantity in a non-dimensional form, the Nusselt number, in terms of the ratio of diameter and length, the Reynolds number and the Prandtl number. You will doubtless agree that this is a significant simplification over the original problem, where I had the dependent quantity depending upon a total of 8 other quantities. And that really is the power of dimensional analysis. Okay. With just simple dimensional analysis, I could have reduced it to 5, but since I recognized that thermal energy is different, I managed to reduce it to just 4. Beyond this point, of course, you cannot proceed by just dimensional analysis. You have to either do experiments or you have to derive correlations analytically, okay, in order to get the relationship between these two. Okay. And these correlations are known now. Okay. For laminar flow, the correlation is that Nusselt number is 1.86 Re per 1 by 3 PR per 1 by 3, okay, D by L per 1 by 3, mu by mu W per 0.14 is what is often added over here. This is something that I will not go through in this lecture. In this case, mu by mu W takes into account the fact that the viscosity of the fluid changes with temperature. Okay. Now, since heat is being conducted, okay, from the bulk of the fluid, okay, to the wall, okay, and then into the shell side, the temperature in the bulk is often different from the temperature at the wall. Okay. It's higher if heat is conducted out, and it's lower if heat is conducted in. Okay. This affects the viscosity of the fluid and therefore the mechanical properties. And this factor, mu by mu W per 0.14, is added in order to take into account this variation in viscosity. Okay. This particular factor we shall not be concerned during the remainder of this course. Okay. You have another correlation for turbulent flow. And the Reynolds number is greater than about 20,000. There the Nusselt number is equal to 0.023 Re per 0.8 PR per 1 by 3 into mu by mu W for 0.14. Okay. You have a different correlation in a turbulent flow. Okay. Now, you can see that for a laminar flow, as the length of the pipe increases, the Nusselt number actually decreases. Okay. So the marginal utility of a long pipe decreases as the length keeps on increasing. Okay. And during this course, we shall see how to derive this relationship. Okay. We shall see how to derive this relationship based upon the microscopic details of how energy is transferred, okay, at the microscopic level. Okay. We shall not go into turbulent flows, but I will try to motivate this kind of a relationship for you in the later lectures, where we consider turbulent flows. Okay. So, there is a considerable reduction, but we still need to do some more work to get these functional forms. Okay. Why does it have to go as Reynolds number to the 1, Prandtl number to the 1/3, okay, or d by L to the 1/3? Okay. Why does it depend in this particular manner? Okay. That is something that we shall discuss in this course. So far in dimensional analysis, we have considered the whole system, okay, as a unit, and we have tried to write down average correlations for this entire system. Okay. In the rest of this course, we shall deal with the local transfer of heat based upon the local temperature. So, let us take one more example, okay, a mass transfer. From a particle. Okay. So, we have, let us consider a spherical particle for simplicity. Okay. There is some species, okay, with concentration Cs on the surface, okay, and we will consider the concentration at far away from the surface, okay, to be C infinity. Okay. And there is this concentration difference. Okay, so if I plot as a function of distance from the surface, okay, if I plot the concentration at the surface is larger and then it decreases as you go away from the surface, okay, for this particle. This difference in concentration results in a flux across, okay, the surface, and therefore, for example, in the problem of the spray dryer, the droplet dries because of the moisture at the surface has a higher concentration than the moisture in the bulk, and that causes a transfer of moisture and the droplet dries, okay, as time progresses. Okay. Now, of course, if it were just a simple droplet that were drying, then the rate of drying would depend only upon how fast the moisture diffuses from the surface to the bulk. But as in the spray dryer problem, the particle is also moving with some velocity u. Okay. And the fact that the particle is getting swept through the fluid, okay, can distort the variation in concentration around the particle. Okay. The fact that the fluid is getting swept around the particle will distort the concentration variation around the particle and could significantly enhance the rate of diffusion. Okay. And that is what we will try to analyze over here. So, for this mass transfer problem, the dependent variable is of course the mass flux J. Okay. The mass flux is the rate of transfer of mass per unit area per unit time. Okay. So, this is equal to the rate of transfer of mass per unit area per unit time. Okay. This of course will depend upon, firstly it will depend in general on the diameter of the particle, okay, with dimensions of length. Okay. It will depend upon the concentration difference between the surface and the bulk, okay, that is Cs minus C infinity. Okay. If this is positive, then there will be drying of the droplet. If it is negative, there will be moisture getting absorbed into the droplet. Okay. In this particular case, it should be noted that what I mean by concentration is the concentration of water in the gas phase on the surface of the droplet. Okay. So, it is not the concentration within the liquid. We assume that the liquid at the surface is in equilibrium with the gas phase at the pressure which corresponds to the saturation pressure. Okay. So, what we mean here is the concentration in the gas phase at the surface, okay, the equilibrium concentration which is given by thermodynamic, okay, relations. Okay. So, this has dimensions of mass per unit volume. Okay. Concentration has dimensions of mass per unit volume. Okay. What can also affect this is the diffusion coefficient. Okay. Diffusion coefficient, if you recall, we derived it from Fick's law of diffusion, that J is equal to d delta C by L. Okay. This had dimensions of m L power minus 2 T inverse is the dimension of diffusion. Delta C has dimensions of mass length power minus 3 divided by length. Okay. And from that, okay, you can see that the mass dimension cancels out on both sides, okay, and you find the dimension of the diffusion coefficient to be length square T inverse. Okay. So, that is the diffusion coefficient. And of course, you also have the mechanical properties, because that relates to how fast the droplet is moving through the fluid. So, therefore, the mechanical properties are also important for the fluid. Okay. The rate at which the transport will be affected, of course, by the fluid. You know that when fluid flows past a surface, the rate of transport increases. So, it depends upon the velocity. And the mechanical properties of the fluid. In this case, it will depend upon the density and the viscosity. Once again, here we can make a simplification. Okay. The simplification is that when we talk about mass transfer, we are talking only about the mass of the solute, whereas when you are talking about mechanical properties, the density, the viscosity, etc., we are talking about the mass of the entire fluid. Okay. So if there is no interconversion of mass between the mass of the fluid and the mass of the solute, we can consider these to be two different things. Okay. As far as mass transfer quantities are concerned, the dimension should be the mass of the solute, whereas when there are mechanical quantities are concerned, the dimension should be the total mass of the fluid. Okay. So let us write another dimension for the mass of solute alone, okay, and we will write that only for the mass transfer quantities, that is the flux, okay, and the concentration difference. Okay. These alone depend upon the mass of the solute, whereas the mechanical quantities here depend upon the mass of the fluid. Okay. So we have 7 quantities. Okay. Originally we just had mass, length and time, okay, 3 dimensions, and therefore we should have 4 dimensionless groups. Okay. Whereas once we written it in terms of the mass of solute, we have now 4 dimensions, and therefore one can get only 3 dimensionless groups. Okay. So that is the simplification that we bring about when we recognize that there is no interconversion of mass between the solute and the fluid. Okay. So we should have a total of 3 dimensionless groups here. Okay. One is the dependent dimensionless group. The dependent dimensionless group in this case is a non-dimensional flux. Okay. The non-dimensional flux has dimensions of mass, length and time. There is mass of solute, length and time, and that has to be combined with quantities which are related to the mass transfer. Okay. So quantities related to mass transfer are the diffusion coefficient, quantities related to mass transfer are the diffusion coefficient, the concentration difference, and of course the diameter of the particle. So I will write my dependent dimensionless group, okay, as equal to the mass flux, okay, the concentration diffs per A, the diffusion coefficient for B, and a length scale, a diameter per C. Okay. And from the dimensions of the mass of solute, the length scale and the time scale, I will find out what are A, B and C. Note that I have done the simplification in such a way that this expression does not contain in it the total mass of the fluid. Okay. So therefore I have ms per 0, L per 0, T per 0 is equal to ms L per minus 2 T inverse into ms L per minus 3 per A. Okay. The diffusion coefficient has length square T inverse per B, okay, and then I have the length per C. Okay. So with this I can get all 3 quantities A, B and C. Okay. So 0, if you take just the mass of solute dimension, okay, I will get that 0 is equal to 1 plus A. If I take the length dimension, okay, I will get 0 is equal to minus 2 minus 3A plus B plus C, and finally the time dimension will give me 0 is equal to minus 1, okay, minus B plus C. Okay. And this you can solve relatively easily. Okay. First thing you will get is that A is equal to minus 1. Okay. You will get B equals minus 1 and C equals plus 1. Okay. I should rewrite that. Okay. If I take the time dimension, I will get 0 equals minus 1, okay, and minus B. There is no C in that, okay, because there is only 2 time dimensions there. Okay. So, therefore, the dimensionless group is equal to J d by d delta C. Okay. Okay. And this also I could very well have known that from just Fick's law of diffusion. Okay. Fick's law of diffusion states that the mass flux d delta C by L. Okay. This is of course applicable only locally at every point within the fluid. Okay. However, the dimensions on the left and the right are the same. Okay. This law of diffusion is not valid for the entire system because the mass transport on the larger scale is affected by convection as well as diffusion. Okay. But however, the dimensions on the left and the right are the same. So, if I could just scale J by something that was d delta C by d, I know that that would be dimensionless. Okay. So, there is a first dimensionless number. Okay. The second one, okay, we already know one other dimensionless number, which is rho u d by mu. Okay. The Reynolds number involves purely mechanical quantities. Okay. That is number 2, and there should be one more. The third one should involve both thermal and mechanical quantities. Okay. I am sorry, both mass transfer as well as mechanical quantities. Okay. Quantities related to both mass diffusion as well as with respect to momentum diffusion. Okay. We can assemble that, okay, by considering the diffusion coefficient along with mechanical properties. Okay. So, if I consider a dimensionless group, okay, phi 3, okay, diffusion coefficient, it has dimensions of length square per unit time. Okay. So, I need to non-dimensionalize that with 2 other mechanical quantities. Okay. In this particular case, I could take them as the density power A and the viscosity power B. Okay. That is the simplest consideration because both density and viscosity have dimensions of mass. Okay. And therefore, I could take it as density power A times viscosity power B. Okay. And from that, I could get a dimensionless group. Okay. Mass, length and time, okay, should cancel out. Okay. In general, I would have to have a length scale as well. Okay. But as you will see, this coefficient turns out to be 0, okay, and I will tell you why later. Okay. So, A, B and C are calculated from the dimensions of length, mass and time. Okay. So, therefore, once again m power 0, L power 0, T power 0 is equal to L square T inverse power A, m L power minus 3 power B, C and I am sorry. So, if I take the mass dimension, okay, I will get 0 is equal to A plus B. If I take the length dimension, I will get 0 is equal to 2 minus 3A minus B plus C. And if I take the time dimension, I will find that 0 equals minus 1 minus B. Okay. Therefore, from this I will get B equals minus 1. Okay. Okay, from this relation, and since A plus B has to be equal to 0, I will get A equals plus 1. Okay. And it turns out that C is just equal to 0, okay, if you work it out. Okay. B is equal to -1 and C is equal to, will give you C is equal to 0. Okay. Therefore, the third dimensionless group is equal to rho d by mu. Now, I could very well have scaled, okay, the diffusion coefficient by the particle diameter and the velocity as well, okay, in which case I would have got a different dimensionless group. Okay. But in this case, what I have tried to do is to make sure that there is only one quantity which depends upon the particle velocity. Okay. There is only one quantity which depends upon the particle velocity, and this other one is just a material parameter. Okay. It does not depend upon the particle diameter or the particle velocity. Okay. This is just a material parameter. Okay. These also have names. Okay. The first one, J d by d delta C, okay, it has to be some function of, okay, and rho d by mu. Okay. It is conventional to write this third dimensionless group pi 3 not in this fashion, but rather as its inverse. Okay. Pi 3 is usually defined as mu by rho d. Okay. Okay, that is conventional, and this is what is called the Schmidt number. Okay. It's called the Schmidt number. Okay. Therefore, what I have on the left hand side, this one, the dependent quantity, the non-dimensional flux, it is called the Sherwood number, is equal to some function of, this first one is the Reynolds number and the second one is the Schmidt number. Okay. So, in this problem, whereas I had a total of 7 quantities initially, I have reduced it to just 1 dependent and 2 independent quantities. Okay. Beyond this, of course, you cannot progress by just dimensional analysis, you have to go to correlations. Okay. And correlations, for example, are typically for low, okay, Reynolds number and Schmidt number. The Sherwood number is written as 2.0 plus 0.6 RE per half SC per 1/3. Okay. So, in the limit as the Reynolds number goes to 0, this Sherwood number just goes to a constant value. Okay. Why is that? We will see as we go through the course. Okay. At high Reynolds number, Reynolds number for laminar flow. Okay, I should. Okay, the Sherwood number is written as 1.25 RE per 1/3, okay, SC per 1/3. So, these are the kinds of correlations that you have between these non-dimensional quantities. Okay. And in this class, we will see how to derive these kinds of correlations, okay, Sherwood number correlations, okay, for both high and low Reynolds number. Okay. In the next lecture, I will try to demystify these dimensionless numbers a little bit. Okay. We managed to get dimensionless numbers in terms of the Reynolds number, the Schmidt number, the Prandtl number, and so on. What do these physically mean? Okay. So, I will try to give you some physical insight into what these dimensionless numbers mean and why the relations that we have are of this particular form, okay, for mass and heat transfer, as also the drag coefficients for momentum transfer. Okay. So, I will try to give you some insight into that. Okay. But before that, I will do one problem which involves the power on an impeller, okay, to illustrate how scale up is done, how these dimensionless group can assist us in scaling up, okay, from small systems to large systems. What are the kinds of things that are to be maintained constant when you increase the size of a system? Okay. Obviously, you have to scale up in order to have economical processes, but it's not straightforward to do it. If you have something that works in the laboratory, it is not clear that it will work in an industry. Okay. So what are the considerations there? Those scale-up considerations I will talk about first, and then I will come back and try to give you some physical idea of what these dimensionless groups mean. We will see you in the next lecture.